Good morning, students and friends. So in this video, we'll be learning about second order system. We'll be uh, understanding about second order system, and we will. Uh, I'll try to motivate you why we study all these maths and what are the physical applications for this. So content is we'll consider a typical second order system. Then we'll understand about the parameters of a typical second order system. It is completely characterized by two parameters, theta and omega n. And then we'll see about step response of underdamped second order system, critically damped and overdamped. Then the most interesting part, which I am sure all of you will appreciate, is the practical examples. So a typical second order system is given by the transfer function omega n square divided by s square plus 2 theta omega ns plus omega n square. I hope you recall our periodic table example. So if you know group 1 element, you know about all group 1 element. If you know group 2 element, you know about all group 2 element. So the idea here is we'll study this second order system, and then the thing is that you know all second order systems. So that is why we are giving so much importance of this. Here, omega n is called the natural frequency of oscillation. Omega n is called the natural frequency of oscillation. So here you see omega n, and you note here that here also it is omega n square, here also it is omega n square. And then there is this theta. Theta is called the damping ratio. Both of them are important. And I have told you in passing about one technical term which will come quite often, are called the poles. Poles of the transfer function corresponds to situations where the denominator becomes 0. It's very important, so that's why I'm writing it slowly. So this is our transfer function. The denominator will become 0 when s square plus 2 theta omega ns plus omega n square is equal to 0. So from our school maths, we know that ax square plus bx plus c equal to 0. The roots of the characteristic equations are minus b plus or minus root of b square minus 4ac by 2a. So when you simplify it, you will get the poles as this. For the system, the poles are this. I assume that theta is less than 1. So when theta is less than 1, these are the poles, where j is root of minus 1. So we say that when theta is less than 1, you can look here. When theta is less than 1, say theta is 0.5, this becomes s square plus omega ns plus omega n square. So the roots will be complex. So poles are important, and so we'll come to see about poles more later. I want to use minimal mathematics in this presentation. I have given you another presentation where I derived everything. So this is minimal math, so that I want all of you to understand and appreciate this talk. So let us consider an undamped system. For undamped system, we could find step response to be c of t is equal to 1 minus e power theta omega n t divided by root of 1 minus theta square sine omega dt plus phi, where omega n and theta is given. So from that you can compute omega d. Omega d is what is called damped frequency of oscillation. You can compute omega d. Omega d is omega n into root of 1 minus theta square, and phi also you can compute tan inverse root of 1 minus theta square by theta. Those who are interested, please look into the derivation of this. And if it is critically damped, what is underdamped? Underdamped means theta is less than 1. critically damped case corresponds to theta equal to 1. When theta equal to 1, you see the response is given by this expression, 1 minus omega nt e power minus omega nt minus e power minus omega nt. So from this you can see that as t goes to infinity, what can you say about this term, e power minus omega nt? When t goes to infinity, e power minus omega nt will become 0. And again, this term also will become 0 when t goes to, because t is increasing and e power minus omega nt is decreasing at a faster rate. The net effect will be these two terms will become 0. And when you give a step input to a second order system, the output will be again step. And that feel you should have here also. That feel you should have here also, where this term e power minus theta omega nt, this term will become 0. So for underdamped or critically damped, the final value of the step response is 1. And for overdamped system, we could derive it as CFT is 1 minus omega n square divided by S1 into S2 minus S1, which are the poles, e power minus S1t and some constant into e power minus S2t. So basically this also is saying that as t tends to infinity, these two terms will decay to 0, okay, and the output will be 1. So let us see figures, okay. So these derivations are easy. I would recommend that you do the derivation. As I have said, ad infinitum, Cs by Rs is omega n square divided by S square plus 2 theta omega ns plus omega n square. So Cs is Gs into Rs, you take Ct is L inverse of Cs. You can derive this. I would recommend that all of you do the derivation. I have derived it in the last class. Let us get the feel, okay. That the major objective of this talk or lecture is, I am giving this to a wider audience, okay, is for you to understand the physical significance of step response of second order system. We know that the expression for second order step response is e power minus theta omega nt for underdamped case. So this term will decay off to 0. And what is this term? There is a sine omega dt plus phi. All of you being electrical engineers or mechanical engineers, you know the shape of sine curve. And what is happening to this sine curve? As time goes to infinity, that sine is decaying. So that is why our step response is having this shape. For underdamped system, the step response has a sinusoidal component which is dying out. So we can think of many practical examples where this kind of phenomena could be seen. Like you give a step input, there will be some oscillation and it will die down. So if for critically damped system, here it is written critically damped system. For the critically damped system, we have seen the expression 1 minus omega nt e power minus omega nt and another e power minus omega nt. So for the critically damped system, the response will be like this. So there is no sine term. So there is an exponentially decaying term coming up, and it becomes 1. So if you are you could generate this once you know the transfer function, you know omega n, and you could draw a table. You can write C of t here, then corresponding to, you can write time here, and you can compute all the values of C of t. You can write it in Excel and you can plot C of t versus t. You will get this graph. I would recommend that you do it. Or if you know MATLAB, you can write a very one-line program, or in Python, whatever. You could. I would recommend that you draw the plot. Okay. And for overdamped case, we have seen the response. The expression is this. So there are two decaying terms. and finally initially these 2 will be 0.5, so 1 minus 0.5 will be 0, and as time goes on these negative terms will vanish and you will get the response like this. This is called overdamped system. So the point is the following: why we study second order systems? Many systems shows nature of second order. Let us consider a very simple example, and you could do this in the lab. Resistance is something which is very comfortable for you. You can take a resistance in our systems and control lab. You can take an inductance of any value. You can take capacitor, put it on a breadboard. You give a square wave here. You give a square wave. Low frequency square wave. So low frequency square wave is equivalent to a step. Then you can see the output. What is the transfer function for this? The transfer function for this we have seen earlier is E0s by EIS is 1 by LC divided by S square plus R by LS plus 1 by LC. So here this 1 by LC is what? 1 by LC is omega NC, omega n square, and R by L is what? 2 zeta omega n. So if you increase or change R, the damping will increase. So when you give a step input, you take an oscillator, you take a CRO, oscilloscope, you connect a square wave here, and you connect this output E0t to a CRO. Once you connect this to a CRO, what will you see? You will see the output as we saw in the last slide. And I have simulated this in MATLAB, and you will get the response like this. When R is a small value, 100 ohm, the response will be oscillatory. When R increases, say 1K, the response became a little sluggish. And when R increased further, the damping is too high. So this is a practical example where you could see the effect of damping. Here the damping is decided by the value of R. So you could simulate this in MATLAB, or you could do as I told you in the lab. And in fact, our students are doing this in the lab, and I hope you have done this at least using MATLAB. Okay. So why we study about second order system is not just to understand about RLC network. Many systems, many practical systems exhibit second order characteristics. You know, you have seen ammeter, isn't it? And in ammeter, the input to the ammeter is current, and output of the ammeter is the reading. You see the needle deflection, isn't it? So if you take a 0 to 10 ampere ammeter and you apply, say, 2 ampere, or you apply 1 ampere unit step, you might have noticed that it will not show 1 ampere immediately. What will happen? This is the ammeter, you are in the lab, and you will see that if you send 1 ampere, so it will the needle will oscillate, isn't it? This is the needle. The needle will oscillate. So what is the output? The output of the ammeter is theta. Input is current. So we can derive the transfer function, and you have studied in measurements about dynamic characteristics of moving coil galvanometer. So it's a second order system. So there, if the damping is more, what is the good for the ammeter? There will not be any oscillation. If damping is large, what will happen? If you send 1 ampere current, it will show 1 ampere only after 10 minutes. So that is not good. And if you send 1 ampere current and if it oscillates, that also is not good. So we want for the ammeter, the damping to be, we want the ammeter to be damped properly. Even critically damped is not good damping. So it is found that damping ratio of 0.7 is good, and it depends on application what you are doing for. Okay. So I hope you understood the ammeter example. So why we study all these things? Because if you are designing an ammeter, if you want, you can simulate the ammeter, and you can decide how much damping should be given. If damping is very small, what will happen? The ammeter will keep on oscillating. You send 1 ampere current, you have to stay there for a long time to see the correct reading. If the damping is more, you send 1 ampere current, there won't be any oscillation, but it will slowly reach 1 ampere. So we don't want that to happen. Okay. So another example is weighing machine. Okay, you are say being COVID, grown fat. I think I'm 75 kilos. If I stand on the weighing machine and look, the weighing machine will not show 75 immediately. It will show 76, then it will oscillate to 74, then it will go back to 75.5, 74.5. It will oscillate and finally settle at 75. So here it's not unit step. The step input is of magnitude 75. So this you would see anywhere, like if you go to a grocery shop, and now those kind of weighing machines are not there. If you look at the weighing machine, there will be, the needle will oscillate. This oscillation is characterized by our 1 minus e power zeta omega nt by root of 1 minus zeta square sin omega dt plus phi. So any instruments have this second order characteristic. Not only that, second order is so important that any system you could assume it to be second order. Any system you could assume it to be second order. Like I told you about the poles of the transfer function. Any system will have many poles. Second order system will have 2 poles. First order system will have 1 pole. Third order system will have 3 poles. And nth order system will have n pole. Of this, the most dominant, we can take the most dominant. We can approximate higher order system by second order. And then all these delta, theta and omega n has significance there. Okay. So I'll give you an example of power system. So in a power system, the input is, you have all seen Idiki hydroelectric power station. So when they want to increase the generation, they will open the nozzle. When they open the nozzle, that is equivalent to having a sudden inrush of water. So that is the input. And what is the output? Output is the frequency. We want the frequency to be 50 hertz. So usually what KCB engineers will do is, this problem is called load frequency control. When the frequency comes down, they will open up the valve. So this opening up the valve is equivalent to step input. I'm simplifying it extremely, but the physics is same. I'll open up the valve, then there's a sudden inrush of water. Then what will happen? The frequency will go up. So you'll see that the frequency will have an oscillation of this kind. If I plot the delta f, you'll see that 50 hertz it was. So I'm not plotting absolute frequency. I'm plotting the deviation in frequency. The frequency was 50 hertz, 49 hertz now. Then when I give a slight change in the input, then the frequency will oscillate and settle down. This phenomena could be there in many examples. So let us consider one concrete example. Consider a system with transfer function 25 by s square plus s plus 25. Find theta and omega n. Obtain the expression for step response. Try to do this, okay? So I'll tell you theta is, omega n is how much? Square root of 25. And omega n is 5. If you substitute theta omega n is 1, so you'll get theta equal to 0.1. 2 theta omega n is 1. Omega n is 5. 2 into 5, 10. 10 into theta is 1. So theta is equal to 0.1. So I can get the expression for, I can substitute, so I know omega n, I know theta, I can compute omega d. Omega d is this, omega n into root of 1 minus theta square. So omega n is 5, omega d, the effect of omega d is omega, it will be slightly less than. It's called damped frequency of oscillation, and phi is 1.47. So I'll get the expression for step response. Now I can plot this. So the plot of this will be, theta is 0.1, there will be big oscillations. There will be a lot of oscillations, and finally it will settle to 1. Okay. So this you should try at home. Okay. So B is equal to 0 means damping ratio is 0. B is equal to 1 is damping is small. B is equal to 10 is it is over damped. Try to obtain the response and sketch the response. So this is the summary. This is what you should remember. For most cases, it will be undamped, underdamped system. CFT is given by this expression, omega d. What is omega d? Damped frequency of oscillation, that is equal to omega n into root of 1 minus theta square, and phi is tan inverse 1 minus theta square by theta. And what is omega n? Natural frequency of oscillation. And what is theta? Damping ratio. So this is take home. You will forget all the maths. You will forget omega n and theta. That's okay. But you should know that for a underdamped system, when you give an input, the output will change and settle to steady state after some little bit of oscillation. If it is critically damped, there will not be any oscillation. And if it is over damped, the response will be, if it is over damped, the response will be sluggish. And if it is underdamped and the damping ratio is very less, the oscillation will be too high. If damping decreases, there will be more and more oscillation. If damping is 0, you will get a pure sine wave. I didn't include it, I didn't want to. So this should remain with you like eternity. So that is the take home. Okay. So thank you very much, and thank you for, I put this in LinkedIn. Thank you for very nice feedback, especially by engineer Museem. So that prompted me to put one more video into LinkedIn. Okay. So I hope this would make sense for, I tried to make it self-contained. I hope this would make sense for non-electrical engineers also. So thank you very much.